Look at this crowd reacting to a live performance. Without hearing the music, you can see the physical force of the sound washing over them. Microphones are recording this exact moment, capturing an invisible physical event and turning it into something we can store. To understand this, we have to look at what sound is. Whenever you speak or sing, you push on the air around you, creating physical ripples of varying pressure. The speed of these ripples, their frequency, dictates the pitch you hear. The size of the ripples, their amplitude, determines the volume. That physical pushing of air is the only language human ears understand. But your computer, your smartphone, and your speakers operate strictly on electrical currents and binary code. This creates a severe bottleneck. You have physical air pressure on one side and electrical signals on the other. They are incompatible formats. The microphone functions as a real-time mechanical translator. It catches the precise physical ripples of a human voice and instantly writes them into an electrical language that digital devices can read. You've likely seen a setup exactly like this. Life stages are loud, physically chaotic spaces. Any piece of delicate technology placed here has to survive an unpredictable environment while still doing its job. This simplified cross-section shows the two things a microphone relies on to survive chaos. First, there's a diaphragm, a thin membrane designed to vibrate when those ripples of air hit it. Second, there's a transducer, the engine converting that physical vibration into electricity. To handle the sound pressures of a live concert without breaking, engineers rely on this specific design, the dynamic microphone. Inside the casing, the engineering relies on electromagnetic induction. A tiny coil of copper wire is glued directly to the back of the diaphragm, and that coil sits suspended in the middle of a permanent magnetic field. When physical sound waves push the diaphragm inward, the attached coil slides backward through the magnet. When the air pressure drops, it pulls forward. Moving wire through a magnetic field generates a small electrical current that perfectly mimics the original air ripples. Because it relies on a physical magnet and moving wire, this process is totally passive. The microphone generates its own electricity entirely from the physical force of the singer's voice. This heavy physical mechanism means dynamic mics aren't highly sensitive to microscopic acoustic details. They trade that sensitivity for rugged reliability, making them the structural backbone of live audio. Take that microphone off the stage and put it into an isolated recording studio, and the priorities change. Here, audio engineers need to capture the absolute faintest breath of a vocal take, or the subtle slide of fingers on a guitar string. To capture that level of microscopic detail, you need a transducer with far less physical mass holding it back. You need a condenser microphone. This diagram shows the process. Instead of dragging a copper coil through a magnet, a condenser uses capacitance. It features an ultra-thin metal diaphragm placed parallel to a stationary, solid metal backplate. When sound hits this microphone, that feather-light front plate vibrates. This changes the microscopic distance between the two plates. As the distance fluctuates, their ability to hold an electrical charge fluctuates too, spitting out a highly detailed, precise electrical waveform. However, because those two metal plates must hold an active electrical charge to detect the changing distance, condenser microphones require external power. This is usually supplied as phantom power flowing directly up the audio cable from a mixer. The engineering goes beyond the internal plates. The external shape of the casing is deliberately cut and vented to act as an acoustic lens. This creates specific polar patterns, allowing the mic to selectively reject noise from the sides or rear and only listen to what's directly in front of it. You can see this spatial filtering in a shotgun microphone. This long vented barrel uses phase cancellation to block ambient noise, making it the essential tool to isolate a single actor's dialogue on a busy and loud film set. Every microphone design is a calculated set of trade-offs. Whether tweaking internal electrical plates or shaping external acoustic tubes, engineers build specific tools to cut through acoustic chaos and capture only the target. Once the microphone captures that target, its job is technically done. But the raw electrical signal it produces is weak. If you fed it straight to a hard drive, you'd barely register a whisper. That's where preamplifiers and mixers take over. They grab that frail electrical current and boosts its strength, allowing multiple signals to be balanced against each other before they are recorded. Eventually, that amplified electricity has to be heard by human ears again. It travels down a wire to its final destination, the loudspeaker, and this is where the translation process is completely undone. A loudspeaker follows this exact engineering logic, only in reverse. This side-by-side comparison shows the same physics at play. On the left, a microphone uses physical air ripples to move a coil and generate electricity. On the right, a speaker takes incoming electricity, shoots it through a wire coil to react with a magnet, and pushes a large cone outward, creating physical air ripples. By pinning our physical reality to digital code, the microphone creates a meticulous bridge between those two worlds. It grants us the power to freeze fleeting moments of sound into permanent digital memories.